Okay, so we are going to start 1.1 on limits and continuity. So first we're going to describe what a limit is. A limit is describing the y value that a function approaches at an indicated x value. And when we're thinking about this limit, we're looking at, or analytically thinking about, what is happening to the function as it is a little bit less than that value and as it's a little bit more than that value. So the behavior to the left and to the right of our indicated x value. And that's really giving us the idea of this limit. So we're looking at the y value in relation to a particular x value. Notation-wise, you're going to see limit. This reads the limit as x approaches c of f of x equals L. If we're reading that out loud, that's how you would read that. Some things to note, some properties about limits. So this is saying that this limit does in fact exist. It equals some number L. It is possible that a limit does not exist. We're going to look at specific cases where a limit does not exist. And it's very commonly used, the DNE for does not exist. This happens when the left side of the function is not equal to the right side of the function at that particular x value. Or in terms of the limits, the limit from the left and the limit from the right. Or when the function at the left and or the right is approaching positive or negative infinity. And we briefly talked about left and right, and we're talking about looking at a function, the limit as it approaches from the left versus from the right. And the notation that you're going to see for that, the notation you're going to see from that is the limit as x approaches c, and there's going to be a little superscript and a plus sign that indicates from the right, or a c with a superscript of a minus indicates from the left. If there's no superscript like there was originally in our notation, that just means we're looking at the limit as a whole from both directions, as opposed to one-sided limits would be looking from just the left or just the right, depending on that setup. So let's go ahead and define a second function g of x and find the limit, or state that the limit as x approaches c of g of x is equal to m, so that we can talk about how limit properties work when we have multiple functions. So if we are looking at two functions that both have a limit as x approaches c, so the limit as x approaches c of f of x is L, the limit as x approaches c of g of x is m, then it follows that these algebraic properties apply. If we are adding the limits together, the limit as x approaches c of f of x plus g of x, we can really just look at those limits separately and add them together. So that's going to give us L plus m. Since subtraction is just really the same thing as adding a negative number, the same thing applies if we have L minus m. Similarly with multiplication, if we take the limit as x approaches c of f of x times g of x, we can just multiply those two components. And if we are dividing f of x, the limit as x approaches c of f of x over g of x, we can just divide those two values that the limit is equal to. So all of these algebraic properties can come into play to help us in terms of simplifying using properties of limits. Okay, so now we have the graph of a function, y equals f of x, and we're going to look at that graph to identify different components. So let's just start with this right-hand column, these values. This is something that goes all the way back to Algebra 1, being able to look at a graph and identify a particular value. So this is asking us for the function evaluated at -4. We can look at the graph and right here see that the y value when x is -4 is +1. For -1, when x is -1, f of x is +1. So even though there's an open circle there, that's not the value of the function. The value of the function is that ordered pair. F of 2, if you notice there's an open circle at 2, and unlike at -1, there is nowhere along this line where there is a solid coordinate or where there is an ordered pair. So f of 2 does not exist. There's a hole in the graph at that location. F of 3, similarly, it looks like this is approaching negative infinity, but for purposes of right now, we're going to say that f of 3 also does not exist. And lastly, f of 5. Here's 5 at our function. What is actually happening at 5? The function value is 2. So that should have just been a little brief review of looking at a graph to identify the value at an indicated x value. Now we're going to use the graph to identify limits. So the limit as x approaches -4 of f of x of this graph. So what that means is, since it's a two-sided limit, it doesn't indicate with a superscript from the left or from the right. We're looking at what's happening around, before, and after x is -4. Well, since the function is continuous, which we'll define later, since it's continuous, both from the right and from the left, the graph is approaching the value of 1. Similarly, for x approaching -1, from the left and from the right, both pieces of the graph are approaching 4. Now, the function isn't 4 when f is -1. We just identified that over here. The value of the function is 1. But what is it approaching from the left and from the right? Right before we get to -1 and right after we leave -1, we are approaching the y value of 4. So the limit is what it is approaching from the left and the right. When x equals 2, right before we get to x equals 2 and right after we get to x equals 2, both sides of that limit are approaching the y value, or the function value, of 1. When we look at what's happening around x equals 3, well, on the left it's going to -infinity, on the right it's going to -infinity. For right now, we're going to leave that as does not exist. We're going to talk about what's happening with infinity in a different section. But for right now, we're just going to say that function doesn't exist. It's not approaching a specific finite value. And as x approaches 5, from the left and from the right, we're getting different values. So if you look from the left, it looks like it's approaching -1, but from the right, it looks like it's approaching 2. So since it's approaching a different value from the left and from the right, the whole limit does not exist. However, what we just said is that each individual side does have a limit. From the left, the function is approaching -1, and from the right, the function is approaching +2. So what you'll notice is the overall limit as x approaches 5 didn't exist, and it didn't exist because the limit from the left and the limit from the right are not the same value, which is something we're going to define a little more solidly as we get into this lesson. Now we're going to talk about how to use a graphing calculator to approximate the value of a limit. And I know if you took Calc AB last year, you know lots of different shortcuts on how to do this by hand for many of these problems. But for right now, I really want to get you used to how to use your graphing calculator to do this. It's possible that you're going to come across limits that you actually don't know how to do by hand, and you might need a calculator to do that. So pause this video, grab a graphing calculator, or pull up Desmos. Although remember that in terms of the AP test, you're probably going to be using a graphing calculator, not an online program like Desmos. So even though it's easier to use, you want to get comfortable using a graphing calculator. So go into the y equals and go ahead and type in that equation or that function. Make sure that you use parentheses as needed. And when you graph that, there's a couple of ways that you can look at the limit. The first thing you could do is you can simply hit second trace, and then it says value is one of the options. If you hit value, we're looking at what happens when x equals 3. And then you can use the left and right arrows to see, so at 3, the function's value is 5.75. It looks like this function is continuous, and it keeps going right around that value. But if you use the arrows to go a little bit to the left and a little bit to the right, or above and below that value, you're going to see that, yeah, from both the left and the right, this value is approaching 5.75. Another way to see this, and something that for me is a little bit easier sometimes, is if you actually hit, while you're on the graph, if you hit second table, it takes you to an XY table. And then you can actually just plug in the numbers around what you're looking for. So 2.9, 2.99, 2.999, 3, 3.001. and look at and see, are those values approaching both from the left and the right the same number? So the table function is often overlooked, but it's a great way to really look at the limit in numerical form without having to maneuver along the graph. So again, two ways to really think about or see the behavior of the graph is to either graph it, use second trace value and look at that specific value, and then use the arrows to see what's happening before and after. The other option is to use the table, which you can get to by hitting second graph, and that will get you into a table where you can plug in values. If you go into that table and it actually won't let you plug in your own values, what you need to do is hit second table set. That should take you to the table setup, and you need to go down and change the independent variable to ask instead of auto. Your calculator's normal settings have it set up to be auto, and you want to change that to ask so that you can control the x values that are going in. So you can follow that same process for 2 and 3 if you want to pause the video and see if you can graph those and find the limits at their indicated values. If you graph sine of x over x and you look at the limit as x approaches 0, the first thing you're going to notice is if you tried to use the strategy where you graph and trace that value, it's not going to exist. It's going to tell you that your graphing calculator has an error. That should make sense because what you're looking at is having sine of 0 over 0, and that really doesn't make any sense. That's going to be undefined. Now that doesn't mean that the limit doesn't exist, because if you remember from the problem that we did looking at the graph, it's possible that the function value is an open circle, but that what it's approaching from the left and what it's approaching from the right are actually the same number. So I think it's easier on this one, especially to use the table value. So graph sine of x over x, hit second table, and then start plugging in values really close to 0. If you plug in negative 0.0001, negative 0.001, negative 0.01, 0.1, if you start looking a little after 0, 0.0001, each of those values, I think you're going to notice I'm seeing 1, 1, 0.9998, 0.99983, 1, 1. So all of those values really are approaching the value of 1. And this is something that from now on you can just use this fact. It is now a fact that you can say that the limit as x approaches 0 of sine of x over x is equal to 1. You don't have to prove it. You don't have to state why. It is just something you are going to be allowed to use, and that's going to come in handy a little bit later on. And lastly, for number 3, if you graph that function and you look at what's happening on the left or the right, whether that be by actually looking exactly at the graph or looking in the table feature and plugging in values a little before and a little after, you're going to see that this limit is equal to 5 over 4 or 1.25. So this idea of what's happening before and after and at a particular value of a function leads us to the concept of continuity. Is something continuous? And if you think about what that means in the real world, it really means something similar here. Does it keep going? Does it go without breaking? And in terms of a function, you can think about that as, could I draw this without lifting up my pencil? So if we look back at our graph, there are definitely pieces of this graph where it is continuous. But there are pieces where I would have to pick up my pen to go down to that point. There are pieces where it is not continuous. So thinking about whether or not you have to pick up your pen or your pencil helps you identify if something is continuous. So if we're going to formally identify or formally define this idea of continuous, we're saying as x approaches any x value, we're going to call that x value c, the function must approach f of c. And that value has to be defined. So what we're saying is what's happening to the left of the function, what's happening to the right of the function, and what's happening exactly in that instant of c is the same. So the function value is the same, and the limit from the left and the right are both equal to that particular value. So symbolically, f of x is continuous if the limit as x approaches c of f of x is actually just what you get when you plug c into that function. That's how we define continuity. And continuity is a topic that's going to be with us all year long. We really need to understand how to use it and how it works. So we're going to just briefly review a couple of things from previous classes, just sort of as reminders, looking at each value and deciding where it is not continuous, and then stating that interval where it is in fact continuous. So go ahead and take just a minute, answer 4, 5, and 6, think about where it's not continuous, and then come back to the video and unpause. So here on number 4, obviously x equals 5 would be a value where this is not continuous, because that would make the denominator of this function 0. So we're setting up the interval -infinity to 5, that u meaning the union of 5 to infinity. And it does specifically say to state the interval, so you should use interval notation. Typically on the AP test or on a regular test, if it doesn't specify, you can use any notation you want. I know a lot of people prefer to write all real numbers except for 5. In any case where it doesn't say state the intervals, it would be acceptable for you to write your answer in that way. If the directions specifically say interval, then the answer should be in interval notation. 5, we already talked about how x cannot be equal to 0, so that interval is -infinity to 0, union with 0 to infinity. Remember, all of these should be parentheses on the ends of the interval, not square brackets. And then number 6, the denominator would be 0 if x was equal to positive or -3. So -infinity to -3, then the interval from -3 to 3, and the interval from 3 to infinity. So things that create discontinuities are things that we worked with way back in Algebra 2. They have specific names for each type of case. So let's talk through those a little bit. A hole would be when we have an open circle in our graph. So graphically, the function exists, but at some certain value, there's an open circle on the graph indicating that there's a hole. What that looks like in terms of an equation is that we have a factor that divides out. So if you think about x squared minus 9, that would factor to be x plus 3, x minus 3. So the x minus 3's would divide out. That would give us a new function that we're looking at graphically. However, there would be a hole because it's still not possible for that function to exist when x is equal to 3. So we would say here that there is a hole for this particular function at x equals 3. It is still true that a limit exists at this value, and I think that's really important to note. The limit exists because what's happening to the left and what's happening to the right is the same. We're approaching the same value from the left and the right. It just so happens that the function doesn't exist at that particular value. So it's not continuous because it has a hole. However, it does still have a limit at that value. Another type of discontinuity is a jump discontinuity, and it means exactly what it says. It breaks from one piece to another. We usually see this in something like a step function, where one part of the function over a particular portion of the domain is defined in one way, and in another way over the rest of the domain. So a jump would look literally like your graph has a piece going from one place to the next at a particular value. You'd have to lift your pencil, so obviously that would be a discontinuity. Here, if you're thinking about the limits, a two-sided limit is not going to exist, but it is possible that a one-sided limit does exist. So, again, a two-sided limit is not going to exist at that value where it's jumping because it's going from one value to another. It is possible that a one-sided could exist. It's also possible that it might be something weird might be happening at that particular value. Asymptote is probably the one you're the most familiar with. If a function is approaching some vertical line that it's never actually going to touch, but it's getting closer and closer and closer, that is a type of discontinuity in the sense that if the function continues to do something else on the other side of the asymptote, it is creating a break in the function. So a vertical asymptote within a function that exists both on the left and the right of that vertical asymptote, the limit does not exist. We will talk about later how you can write positive infinity, but for right now, I just want you to say that the limit does not exist. The last type of discontinuity is an oscillation, and something I just want you to note, this little asterisk, this is not on the AP test, so you don't actually have to know it for purposes of what you're going to be assessed on, but it's good if we're just talking about the different types of continuity or issues with functions, just to talk about a little bit. So the values appear to approach two or more values at the same time. That's what's happening here. So if you actually want to see an example of this, just because you're curious, if you graph y equals sine of 1 over x on a calculator, and then again, I'm more comfortable with the table feature, you go into the table and you start typing in values around x equals 0. So if you type in x equals 0, it's going to tell you that there's an error. But if you type in 0.001, 0.01, negative 0.01, those values are not approaching the same number like we have seen with other limits, like on the page before we were looking at those first three examples. So this is called an oscillation that creates something where the limit does not exist. But again, this is not going to be covered on the AP test. You're not going to be specifically assessed on it in this class, but it's nice to just mention it. The last thing to note before we move on to just a few more examples is that some of these discontinuities are removable and some of them are not. So removable means that the function still has a limit. So removable discontinuities occur when the function still has a limit, aka when there is a hole in the graph. Then there's still a limit, so even though the function is discontinuous, there is still a limit at that value. So we call that a removable discontinuity. Non-removable discontinuities occur when the limit of the function does not exist. So that would be when we have a jump, a vertical asymptote, or an oscillation. Again, you're not going to see oscillations in this class. This is the only time I'm really going to mention it for you. Okay, so let's look at this graph and identify the types of discontinuities. So the first thing that I notice, and I like to start at the left and go to the right, the first place that I notice an issue is happening right here at x equals -1. So at x equals -1, there's a hole, which means it is removable. If I continue going on the right side of that value, here's my next discontinuity. That's happening at x equals 2, and that is also a hole. I'm going to use quotations so I don't have to rewrite that. A hole, so it is removable. The next discontinuity is happening at x equals 3. There is a vertical asymptote. It's really common. You'll see on AP tests and graders use VA for vertical asymptote. This is non-removable. And last but not least, the last discontinuity that we see is happening at x equals 5. And it is a jump or step. Either is fine. And that is also non-removable. Okay, I know this lesson is getting long, so this might be a good time. Pause, maybe look over the example problems that start at problem A and come back. I'm going to keep going with the video because I want to make sure we get through this whole section. So the next thing we're going to talk about is direct substitution. Direct substitution basically says if your function is continuous, then by definition the function is exactly the same as the limit of the function is exactly the same as the value of the function when you plug in that number. That is how we defined continuity. So what that means is, if we are looking, like at example 7, our function is 3x squared minus 5. Thinking about what that is, that's a quadratic. A quadratic is continuous, which means we can just directly substitute in the value of 3 to figure out what that limit is. So this is going to be 3 times 3 squared minus 5, which is going to be 22. So we are allowed to directly substitute given the fact that the function is continuous at the value that we're directly substituting for. So on number 7, 3x squared minus 5 is continuous everywhere, which means for no matter what we were plugging in or what limit we were looking for, we could just substitute that number in. If you look at number 8 is not continuous everywhere. However, it is continuous at the value that we are interested at, which is x equals 1. It's not continuous at x equals 3. There's a hole in the graph, so direct substitution would not work here. However, we can use direct substitution at the value of x equals 1. So I'm going to substitute in 1 squared minus 3 times 1 over 1 minus 3, and that's going to give us positive 1, negative 2 over negative 2, which is going to be positive 1. Looking at 9, we know that cosine is continuous over its domain, so we are allowed to simply plug in pi, cosine of pi over 3. You should know these trig functions like the back of your hand, is going to be 1/2. So direct substitution is a great shortcut to use when we know the function is continuous at the value for which we're looking for the limit. So we have talked about how it's helpful if we know a function is continuous that we can use direct substitution. If the function is continuous, that is helpful to us. And if the function is continuous, that means the left and the right limit are the same. So we can actually use this fact in reverse. What we can say is we can define continuity using limits. If the limit as x approaches c of f of x is the same as the limit from the left and the limit from the right, then we can say the function is continuous. So let's just say that again. If the limit of the function from the left is equal to the limit of the function at that value from the right is equal to the value of that function, then we can say that the function is continuous. So now we can define continuity by looking at left and right limits. So let's look at these two examples. It says discuss the continuity of the following functions. So the point of interest here is 1. We're trying to figure out everywhere else we're going to be continuous because each of these pieces is a polynomial in and of itself, which is continuous. But if we're looking at what happens at x equals 1, we're trying to figure out whether or not that's continuous. So let's look at the limit as x approaches 1 from the left, from the right, and what the value of the function is at 1. So if we use direct substitution in the top, the limit as x approaches 1 from the left would be what we get when we plug in 1, which is going to be 3. F of 1, well, that's where we would normally evaluate the function anyways, is also going to be 3. And then if we substitute into this other piece from the right, we're also getting 3. So all of these things are the same. So what we're really saying is the limit as x approaches 1 of the function is equal to the left limit, is equal to the right limit, is equal to the value of the function at 1. So what we can say here is that f of x, and I'm sort of out of room, f of x is continuous since the limit as x approaches 1 from the left is equal to the limit as x approaches 1 from the right is equal to the value of the function at 1. So for number 10, we can state with certainty that f of x is continuous. We're going to go through that same process for number 11. So the value of interest on number 11, again, is 1. So we're going to look at the left limit, the right limit, and the value of the function at 1. So here, the limit from the left is 2, which means the value of the function is 2, since that's where it is actually defined for 1. But the limit from the right is 3, so 2 is not the same as 3, therefore f of x is not continuous because the left and the right limit are not the same. The last thing we're going to talk about is the floor function, also known as the greatest integer function. That is notated using upside down or half braces, half brackets. The way that it works is it's basically that you universally round down, and you can see from the graph at the left each of these values. So the limit as x approaches 1/2, if we look at 1/2 from the left and we look at 1/2 from the right, that's the value of the function there is 0. If you also think about 1/2, if you round 1/2 down to the nearest integer, you're going to get 0. If you look at the graph for x equals 1, that limit does not exist. There's a jump discontinuity there. Now, if you think about the limit as x approaches 5 from the left, so you're plugging in 5, but remember the number you're plugging in is actually not 5. It's less than 5. So this would give you 2 times 5 is 10 minus 3 is 7, but it's something smaller than that, so this is going to give you a value of 6. Go ahead and work through those practice problems and then check your answers when you have time.